Hey everyone, and welcome back to the channel. Today we're diving deep into one of the most famous and explosive volcanoes in the United States, Mount St. Helens. You probably know it for its massive eruption in 1980, which literally blew the top off the mountain. It was a dramatic, landscape-altering event that's still studied today. But have you ever wondered what's really going on beneath the surface? What makes this sleeping giant stir? Most of us think of a volcano as this isolated mountain, a lonely peak with a magma chamber directly underneath it. We picture this giant, underground pool of molten rock just waiting for the pressure to build up until, boom, it erupts. While that's part of the story, it's not the whole picture. The activity of a volcano like Mount St. Helens isn't just about what's happening right below it. It's connected to a much bigger, more powerful system of forces, stretching for hundreds of miles. Today we're going to explore a fascinating idea, that the rumblings and eruptions of Mount St. Helens might actually be influenced by earthquakes and tectonic stress happening far away, in places like California and Oregon. It's like the Earth has this intricate network of connections, where a push in one spot can cause a ripple effect that wakes up a volcano hundreds of miles away. So, grab your virtual hard hats, because we're about to uncover the hidden geological drama that links distant quakes to this iconic volcano. To really get this, we need a quick refresher on plate tectonics. Imagine the Earth's surface isn't one solid piece, but is broken up into several giant, rigid puzzle pieces called tectonic plates. These plates are constantly moving, grinding against each other, pulling apart or crashing into one another. The west coast of North America is a super active zone where this is all happening. Specifically, we have the small Juan de Fuca plate being forced underneath the much larger North American plate. This process is called subduction, and it's the primary reason we have the Cascade Range of volcanoes, including Mount St. Helens, Mount Rainier, and Mount Hood. As the Juan de Fuca plate dives down, it heats up, and water trapped in the rock is released. This water lowers the melting point of the mantle rock above it, creating magma. This magma is less dense than the surrounding rock, so it rises, forming the magma chambers that feed our volcanoes. So, subduction is the engine. It's what creates the magma in the first place. But what pulls the trigger? What determines when an eruption happens? For a long time, scientists focused on the local pressure cooker model, the idea that the magma chamber just fills up until it can't hold it anymore. But new research is showing that the timing might be linked to external forces. Think about it like this. Imagine you have a soda can that's been shaken up. It's full of pressure, ready to explode. Now, if you just leave it on the table, it might sit there forever. But what happens if you squeeze the can, even just a little? That extra stress could be just enough to cause the pressurized soda to burst out. In this analogy, the shaken-up soda can is the magma chamber beneath Mount St. Helens, filled with gas-rich magma. The squeeze comes from the movement of the tectonic plates around it. The entire region, from Northern California up through Oregon and Washington, is under constant stress. The North American plate is being squeezed and compressed by the Pacific plate to the west and other forces. This creates a massive field of stress across the entire crust. Now, here's where it gets really interesting. Scientists started noticing a pattern. They looked at the timing of eruptions and periods of increased activity at Mount St. Helens, and compared them to the timing of significant earthquakes happening elsewhere along the coast. They found that sometimes after a large earthquake in, say, Northern California, Mount St. Helens would show signs of waking up. It wouldn't necessarily be an immediate massive eruption, but there would be an increase in smaller earthquakes under the volcano, changes in gas emissions or slight swelling of the ground. All signs that magma was on the move. So, how does a quake hundreds of miles away affect a volcano? When a big earthquake happens, it's not just a local event. It releases a massive amount of energy and instantaneously changes the stress on the surrounding crust. It's like a huge geological reset button. The crust in one area might get compressed, while another area, even far away, might get stretched or unclamped. Imagine the Earth's crust as a giant, brittle sheet of rock. An earthquake is like a crack forming and slipping in one part of that sheet. That sudden movement redistributes the stress across the whole sheet. If the magma chamber under Mount St. Helens is already pressurized and ready to go, A distant earthquake could change the stress field around it in just the right way. It might reduce the confining pressure, the clamping force, that's holding the magma down. It's like slightly loosening the lid on that shaken soda can. This tiny change could be the final nudge that allows the magma to start rising towards the surface. This isn't just a wild theory. Scientists use incredibly sensitive GPS stations and seismic sensors to measure the movement and stress of the Earth's crust in real time. They can actually model how the stress from an earthquake in one location propagates and affects other areas. These models show that stress changes from distant quakes are indeed felt at the location of volcanoes like Mount St. Helens. For example, a study might look at the period following the 2002 Denali Fault earthquake in Alaska, a massive magnitude 7.9 quake. Even though it was thousands of miles away, its seismic waves traveled across the continent and temporarily changed stress conditions in many places, including volcanic regions. Researchers found subtle changes in seismic activity at several U.S. volcanoes, including Mount St. Helens, in the hours and days following that quake. This shows that the crust is far more interconnected than we used to think. It's a dynamic system. So, when geologists are trying to forecast volcanic activity, they're not just looking at the volcano itself anymore. They're also monitoring the broader tectonic environment. They're asking questions like, has there been a recent large earthquake in the region? Has the overall stress in the crust changed? This new understanding adds another layer to the complex science of volcano prediction. It makes the job harder, but it also gives us a more complete and accurate picture of the forces at play. We're moving from just looking at the symptoms of a volcano, like ground swelling and gas, to understanding the larger environmental factors that could be influencing its behavior. So what does this mean for us? It means that the story of Mount St. Helens is not just a local one. It's part of a grand, continental-scale narrative of plate tectonics. The same forces that cause earthquakes in California are part of the system that loads the stress on the magma chamber beneath Washington's most active volcano. It's a powerful reminder that on a geological timescale, everything is connected. The ground beneath our feet is a single, dynamic, and sometimes violent system. The next time you hear about a big earthquake on the West Coast, think about that ripple effect. Think about how that sudden release of energy is traveling through the crust, potentially nudging a sleeping giant like Mount St. Helens, reminding it of the immense power churning deep within the Earth. The science is still evolving, but it is painting a picture of our planet that is more interconnected and dynamic than we ever imagined. Thanks so much for watching and exploring this incredible geological connection with me today. It's a fascinating topic that really changes how you see the world, doesn't it? If you enjoyed this deep dive and want to learn more about the amazing forces that shape our planet, make sure to hit that like button and subscribe to the channel so you do not miss our next adventure. Let me know in the comments what you think. Is this connection surprising to you? I'd love to hear your thoughts. Until next time, stay curious,